Most people step over it, mistaking it for a plain white stripe in weathered rock. But a quartz vein crossing exposed granite at mid-slope elevation, especially one with even the faintest glimmer, can hide thousands of dollars in native gold. It's not always the glint that gives it away. Sometimes it's the location, a vein that persists across fractured bedrock at a subtle angle, where runoff concentrates and erosion has done just enough to reveal a sliver without dislodging it. This specific vein lay within walking distance of an old forestry trail, where snowmelt runoff carved shallow rills into decomposed granite. At first glance, the quartz was typical opaque, blocky with conchoidal fracture faces, but under angled sunlight, a soft, butter-yellow flash held its brightness even when shadowed. Unlike mica, which scatters light in flakes, this glint stayed anchored in the quartz itself. That's the telltale sign: embedded, not plated, rich, not reflective. True gold lacks the mirror sheen of pyrite or biotite. It shines warm, not sharp. The real missed opportunity here was access. This vein intersected a slope just above a secondary drainage fork, a classic vector for both waterborne erosion and historical transport. Most casual observers focus on creek beds and tailings piles, but the upper slope exposures are where gold often lingers unharvested, especially when not free-floating in placer form. Gold locked in quartz is less mobile and more likely to remain near its source, exactly what prospectors seek for high-value finds. A careful walk of the ridge revealed more. Secondary fractures off the main vein, small blowout pockets with iron staining, classic signs of past hydrothermal activity. These zones form when superheated, silica-rich fluids permeate cracks in the host rock, cooling to deposit quartz and sometimes, if conditions were right, gold. Where pressures drop suddenly, along faults for instance, these veins crystallize with their payload intact. That's why fault intersection zones remain prime real estate for small-scale gold hunters. Yet just seeing quartz isn't enough. The key is pairing structure with surface signals. In this case, subtle iron oxidation, reddish streaks around the quartz seam suggested sulfide mineral presence. These oxides often signal prior weathering of pyrite, which sometimes acts as a gold host. This, combined with the coarse nature of the quartz and its persistent alignment with a mapped fault trace, raised the probability that the vein wasn't decorative, it was productive. It takes less than a second to miss it, and often a lifetime to learn what to look for. Real gold-bearing quartz doesn't announce itself with sparkle, it telegraphs value through subtler cues: density, fracture habits, and how the embedded metal interacts with light and weathering. The difference between a barren white vein and one worth thousands lies in trained observation, not luck. Start with luster. Gold inside quartz doesn't glitter, it glows. It maintains its shine under overcast light and in shadow, unlike pyrite or mica, which depend on direct angles and break into shards. True gold within quartz presents as irregular streaks, nuggets, or dendritic threads, often partially obscured but unmistakably metallic. These inclusions tend to anchor themselves inside fractures or along grain boundaries, hinting at deposition alongside silica during hydrothermal circulation. Next comes translucency. While not definitive alone, quartz veins that carry gold are frequently milky to semi-translucent, with glassy fracture surfaces that sometimes reveal hidden veins or metallic blebs just beneath. A handheld light can help. Real gold will remain visible even through surface grime, while pyrite often dulls when oxidized. Fracture type matters. Barren quartz tends to break in predictable conchoidal curves with minimal inclusions. Productive veins often show irregular fracture faces with hematite stains, manganese dendrites, or oxidized sulfide halos, each one a possible breadcrumb indicating a mineralizing event. These accessory features don't guarantee gold, but their presence increases the odds. Then there's the weight and hand test. Quartz is relatively light (2, 65G/cm3, so when a piece of vein material feels heavier than expected, it may suggest metallic content. While this is subjective, experienced fieldworkers often rely on the contrast between expectations and tactile feedback as a quick screening tool. Pieces with visible gold can weigh up to 10–15% more than similarly sized barren samples. Another cue is alteration. Gold-bearing quartz is rarely pristine. Look for zones of silicification bordered by chlorite, sericite, or kaolinite, products of chemical alteration from the original host rock. These textures often surround gold-rich veins, especially in shear zones or low-angle faults where heat and pressure drove prolonged fluid interaction. In one telling sample, a 12-centimeter piece pulled from a veinlet showed all 5 indicators: cloudy quartz with irregular fracture, reddish staining, a fine metallic streak visible from 2 angles, and a weightiness that belied its size. When tested with a simple scratch probe, the gold flake resisted pressure, left no powder, and didn't deform like mica, confirmation enough to justify a full field test. Quartz veins don't appear randomly. They thread through the earth along lines of past violence, fault zones, shear corridors, and pressure drops where mineral-rich fluids once surged and cooled. Understanding this geological logic is the difference between stumbling across a lucky piece and identifying a system worth real extraction. In this case, the veins sat along a mapped fault splay near a granodiorite contact zone, exactly the kind of setting where gold deposition thrives. The process begins deep underground. Under tectonic pressure, rock masses fracture and hydrothermal fluids, hot silica-saturated solutions, rise through these openings. As they ascend, pressure and temperature drop, causing minerals to precipitate out. Quartz is usually the dominant mineral because of its solubility in hot fluids, but metals like gold can co-precipitate if conditions are right, especially when sulfide ions, reduced environments, or wall rock chemistry assist the reaction. The key trigger for deposition is called a boiling zone. As fluids depressurize rapidly, gases escape, and metals like gold drop out of solution. These zones often occur between 100 to 500 meters depth in paleosystems, but are now exposed due to erosion. That's why many gold-bearing quartz veins are found cutting through elevated ridges or mid-slope benches, where overburden has been stripped away. This specific terrain had textbook features: a northwest-trending shear zone, visible in aerial LiDAR, intersecting a dome-shaped granite body. Several minor splays extended laterally, forming tension gashes filled with milky quartz. These are ideal traps, where movement opened voids just long enough for fluids to deposit gold. Historical studies of similar districts, like the Mother Lode Belt in California or Western Australia's Yilgarn Craton, show that the richest veins often concentrate at the intersection of major fault lines and brittle host rock. Another critical terrain cue: the presence of greenstone fragments nearby, especially actinolite and chlorite-rich zones. These metamorphosed volcanic rocks can react with acidic fluids, increasing the chance of metal dropout, including gold. Their presence upstream of the quartz outcrop hinted that this wasn't an isolated vein, but part of a broader mineralized system with the potential for multiple pockets. Still, quartz can form anywhere silica-saturated fluids flow, but only certain settings are truly gold-bearing. When a vein cuts across multiple lithologies, shows evidence of repeated opening and sealing evident in banded textures, and lies along a regional structural corridor, it ticks the boxes for further investigation. The surrounding float material, loose rock eroded from the vein, also told a story. Pieces found downhill carried the same signature quartz with subtle metallic traces, confirming that erosion had already begun dispersing gold downslope. The quartz was only part of the message. True gold veins rarely travel alone. They bring companions that act as subtle markers, revealing where heat, pressure, and chemistry converged in the past. In this case, the presence of fine-grained pyrite within fractures, a faint metallic odor in freshly broken rock, and specks of orange weathered chalcopyrite gave strong indications that gold might be more than just visually present. It might be chemically associated. Pyrite, often vilified as fool's gold, is in fact one of the best signposts for real gold in quartz systems. In hydrothermal environments, gold commonly precipitates alongside iron sulfides, especially when the surrounding rock is reactive. In low-sulfidation epithermal systems, gold can occur as submicron inclusions within pyrite grains. Though invisible to the naked eye, these grains can yield serious returns when concentrated and roasted correctly. The trick is knowing how to read pyrite. Euhedral crystals with cubic faces usually form at lower temperatures, while massive granular forms signal more dynamic high-pressure conditions, better odds for gold inclusion. Chalcopyrite, with its brassy yellow tone and occasional iridescent tarnish, is another solid indicator. While its color is often confused with gold, it's more brittle and oxidizes readily. When found in minor amounts alongside quartz and pyrite, especially in vuggy or brecciated textures, it points to a polymetallic vein system, an environment known for hosting gold, silver, and base metals together. In the field, the presence of weathered chalcopyrite turning blue-green due to copper sulfate formation along fractures adds another confirmation layer. Arsenopyrite, though rarer and requiring caution due to its toxicity when heated or ground, is a high-value marker. Its silvery-gray metallic grains, often with striated surfaces, show up in shear zones and are directly correlated with invisible gold in many orogenic deposits. When found in association with quartz and iron oxides, especially in country rock near the main vein, it suggests a more complex mineralizing event that likely carried gold. Even minor minerals carry weight. Tiny crystals of sphalerite, galena, or tetrahedrite may appear in thin veinlets crossing or paralleling the main quartz. These secondary sulfides are often overlooked, but their presence confirms a multi-stage hydrothermal system. Systems with these traits tend to be richer and more vertically extensive, giving the prospector a chance to trace the vein upward or downward to thicker zones. In this vein, subtle zoning was apparent. A central section showed coarse quartz with visible pyrite blebs, while side branches featured finer quartz with limonite staining, a potential oxidation halo from sulfides. Mapping these zones with a handheld lens and simple acid test, HCl reacts with carbonatrich gangue but not with quartz or pyrite, helped define the productive corridor. The first real test happens before a single pan hits water or lab request is filed. It happens with the eye and the hammer. A legitimate gold trace in quartz isn't about how much you see, but what that small signal tells you about the broader system. In this case, the initial sample broke clean from the vein wall with a satisfying snap. Blocky quartz, sharp-edged, flecked with one stubborn metallic dot that caught the light at every angle. That's the first green light, not shimmer but persistence. There's a simple pressure test for visible gold. Using a knife edge or even a fingernail pressed directly against the suspected flake. Gold is malleable. It won't flake or powder like mica, and it won't shatter like pyrite. Instead, it indents or rolls slightly, holding its color and brightness. This sample passed immediately. Even when scraped, the metallic spot held firm and left a faint gold smear on the blade, an unambiguous sign of metallic gold. A closer inspection under loupe magnification revealed two more crucial traits. First, the gold was embedded along a grain boundary, not sitting on the surface. This suggests it crystallized during the formation of the quartz, not added later by weathering or contamination. Second, a faint halo of orange oxide surrounded nearby sulfide grains, likely weathered pyrite, offering more confidence that this system held the right chemistry for gold deposition. Next came the pocket magnet test. A sweep over the crushed sample turned up several fine black grains, magnetite or possibly ilmenite. While not directly linked to gold in this case, these dense accessory minerals help signal the presence of heavier elements and give a sense of the vein's mineral richness. Their location, concentrated near sulfide clusters, aligned with where thermal fluid pathways likely concentrated. But visual indicators alone don't justify deeper investment. A single flake could be a fluke. That's why this first round of sampling needs to go wide but light. The goal is coverage, not yield. From the main exposure, 5 grab samples were taken across a 3-meter stretch, each labeled with GPS coordinates and fracture orientation. A portable field notebook logged visual observations, sulfide content, presence of oxide staining, and approximate density by heft in hand. No single sample was more than 2 kg, light enough to haul, yet representative enough for pattern recognition. In parallel float samples, loose vein fragments found downhill were collected to determine dispersion distance. Surprisingly, several carried similar sulfide halos, and at least one showed microgold under loupe. This hinted at a wider release zone and supported the idea that erosion was already liberating gold into the surrounding terrain. One test added for insurance, a streak plate run. A quick rub of the suspected gold on unglazed porcelain left a dull yellow mark, not black pyrite or white mica. Another confirmation. While not definitive on its own, it provided an extra confidence layer when added to the growing evidence stack. It only takes one wrong read to derail a promising find. A bright flake embedded in quartz might pass the pressure test, show a yellow streak, and still turn out to be worthless. That's the danger of false positives in the field, particularly from minerals like pyrite, chalcopyrite, or even finely cleaved biotite mica. Each can mimic gold in color or texture, but falls apart under scrutiny. The real challenge is how quickly and reliably you can unmask them without expensive equipment. The first trap is pyrite. While its brass-yellow color and cubic habit can fool the eye, its behavior under stress is entirely different. Pyrite is brittle. A hammer strike or edge scrape sends it crumbling into metallic dust. More importantly, it tarnishes. Exposed to air and moisture, it oxidizes into iron sulfates, turning the rock surface red or brown over time. In contrast, gold doesn't corrode or dull. That alone can help distinguish them when examining vein float material along a slope. Still, pyrite does have value as an indicator. In many systems, it forms alongside gold, particularly in zones of high sulfur hydrothermal activity. But visible gold in pyrite is rare. If it's there, it's usually locked within the crystal lattice or fine-grained inclusions, requiring roasting or chemical leaching to release. Field tests can't detect that. Instead, look for clustering. If you see multiple sulfide types, pyrite, arsenopyrite, and chalcopyrite together, it raises the odds that gold is present in association. Chalcopyrite is another deceiver. Softer and more iridescent than pyrite, it often tarnishes to purples, blues, or greens when exposed. While its yellow tone appears similar to gold at first glance, it's distinctly brassy and loses luster rapidly. A steel scratch test quickly reveals the truth. Chalcopyrite breaks down, gold does not. When crushed, chalcopyrite smells faintly metallic and releases powdery residue, not the ductile smear that gold leaves behind. Then there's mica, specifically muscovite and biotite. In bright sunlight, their flat surfaces flash with deceptive brilliance, but under a loupe the illusion vanishes. Mica forms in thin sheets or flakes, peels easily, and reflects light from only specific angles. Its light and weight makes no streak and crushes into dust. Yet it remains one of the most common misidentifications by beginner rockhounds and even some prospectors in early-stage searches. One reliable secondary check is the hardness scale. Gold measures about 2.5 to 3 on the Mohs scale. You can mark it with a copper coin, a steel blade, or even your fingernail under pressure. Pyrite, by contrast, is harder, about 6, so it resists these scratches. When uncertain, carry a simple kit: steel nail, glass plate, and a copper strip. By testing scratch resistance in a controlled sequence, you can eliminate imposters before committing to more expensive assays. For field verification of fine particles, a basic hand lens at 10x magnification can be a powerful filter. Real gold lacks the crystalline symmetry of pyrite. It appears as irregular blebs, filaments, or smeared masses, especially in pressure zones along quartz grain boundaries. Pyrite, meanwhile, often shows sharp edges and cubic or octahedral forms, even in tiny grains. In one particular sample, what first appeared to be a stringer of native gold failed every test. It shattered under light pressure, streaked dark on porcelain, and left a sulfur odor when ground. Under magnification, it revealed angular cleavage planes, a textbook case of misidentified pyrite. It was a setback, but an instructive one. These are the mistakes that refine judgment. A single quartz vein on the surface is just a tip of the system. To turn a surface flash into a mapped opportunity, you have to read the orientation of the vein, trace its run, and examine how erosion has scattered fragments. That's how productive zones are triangulated, not by chance but by structure, float, and direction. In this case, initial mapping revealed something promising. The main vein trended northwest to southeast and dipped shallowly to the northeast, placing its bulk under cover, upslope from the exposure. Strike and dip measurements were taken directly from the exposed face. Using a geologic compass, the vein's strike was logged at approximately 310 degrees true, with a dip of 25 degrees to the northeast. These angles matter because quartz veins, especially those formed during regional metamorphism, often follow pre-existing faults. The shallow dip suggested that more of the vein extended underground toward the higher slope. That's where the richest pockets often hide, just beneath weathered cover where they've avoided surface leaching. The float trail confirmed it. Downhill from the exposure, fragments of vein quartz, some iron-stained, some with sulfide traces, were found up to 50 meters downslope in a fan-shaped scatter. This pattern typically forms when erosion over time releases chunks from a weakly cemented or fractured vein, washing them down seasonal runoff channels. Mapping the spread gave two key insights. The width of the vein likely exceeds 30 centimeters, and erosion has been active long enough to liberate material into a secondary drainage system. That's critical. It implies longevity and therefore potential for accumulation. But more telling were the changes in float material as distance increased. Closer to the outcrop, fragments had sharp edges, clear quartz, and visible sulfides. Farther out, the quartz was more rounded, less distinct, and lacked visible mineralization. That drop-off helps estimate how far gold-bearing material travels before dilution, important for tracing placer sources or identifying secondary enrichment zones. It also narrowed the target zone for further sampling, between 5 and 20 meters upslope, where the vein's projected dip intersects shallow overburden. To verify that alignment, a controlled trenching line was flagged perpendicular to the strike. At 5-meter intervals, shallow scrapes exposed the subsurface. In 2 spots, quartz fragments matching the host vein were found only 15–20 cm below ground, accompanied by slight iron staining and minor sulfide specks. No visible gold appeared in these trench samples, but they confirmed vein continuity, a critical step for eventual repeat sampling and grid setup. Meanwhile, float paths in the adjacent draw told a complementary story. At the confluence of 2 small rills, fine black sand and heavy mineral concentrates accumulated in a small natural depression. When panned, these yielded a small amount of magnetic material, and in one pan, a tiny flattened speck of bright yellow trapped behind a black sand ripple. It resisted swirling, flashed under both wet and dry conditions, and when dried, held shape under needle pressure. It was a microflake, but genuine. Once gold shows up in both vein and wash, restraint becomes as important as curiosity. Overexposing a find, especially one near public access, can invite trouble, from unauthorized diggers to premature interest from local authorities. That's why the first round of serious sampling must balance proof gathering with discretion. The goal is simple: collect enough material to confirm grade and continuity without disturbing the site beyond repair or giving up its exact position. In this case, extraction was done using a hand sledge, cold chisel, and a battery-powered rotary tool fitted with a diamond wheel. 3 targeted notches were cut along the exposed quartz, one at the apparent core where visible gold had appeared, one at the hanging wall contact, and one at the footwall slightly into the host rock. Each cut yielded a 1–2 kg chunk of vein material. Each was bagged, labeled with GPS, photographed, and stored separately. Samples were never left unattended in the field, and no tailings were left behind that might signal active prospecting. Surface recovery was equally calculated. Float material with high sulfide or oxide staining was collected selectively along a 15-meter line downhill from the vein. A soil scoop, 20 classifier, and plastic gold pan were used to isolate heavies in 2 test pans per station. While most yielded only dark sands and minor sulfides, one pan stood out. It returned 2 pinhead-sized gold specks and a few bright sulfide grains. Even without consistent visible gold, this pan confirmed local enrichment, enough to justify further testing without resorting to industrial methods. At the vein itself, direct visual sampling was supplemented with press and lift, adhesive pads, simple field tools for microparticle collection. Pressed against fractured quartz surfaces, these pads can lift fine dust and flakes that settle into microfractures. In this case, gold-colored particles were visible on 2 of the 3 pads. Back at camp under a field microscope, they appeared irregular and dull, good signs. Synthetic glints tend to be smooth or uniform, but native gold flakes reflect the chaotic cooling and fracturing of natural deposition. A second, less obvious test involved UV fluorescence. While gold itself doesn't fluoresce, associated minerals sometimes do. Under long-wave UV, parts of the wall rock adjacent to the vein showed a weak blue-white glow, likely due to scheelite calcium tungstate or feldspar alteration. Though not conclusive, this fluorescence aligned with other hydrothermal systems where gold is known to co-deposit with tungsten minerals. It was one more breadcrumb on the path to a broader understanding. One layer deeper, the collected vein samples underwent a magnet sweep. While gold isn't magnetic, its association with magnetite and pyrite can hint at deeper sulfide networks. Several crushed fragments released strongly magnetic black grains, concentrated toward the footwall zone. This suggested the presence of iron-rich gangue minerals, possible hosts for fine or invisible gold. Still, everything hinged on recovery potential, so a mini-mill setup was built at base camp using a small rock crusher and sluice. Each 1 kg sample was crushed, classified, and panned to identify gold content. Results varied. Sample A vein core gave the best return, 4 bright flakes totaling 0.18 grams. Sample B hanging wall showed only sulfides. Sample C footwall delivered 2 tiny specks, barely visible. That disparity confirmed what many veins show: gold is rarely distributed evenly, and width is no guarantee of grade. For all the effort put into identifying visible gold, many veins hide their true worth in what can't be seen. Free milling gold, loose, recoverable with gravity separation, is only part of the story. In some systems, the bulk of the value lies locked within sulfide minerals, invisible to the naked eye and inaccessible without roasting, flotation, or chemical leaching. And in this case, early signs pointed toward exactly that scenario. After crushing and panning 3 key samples from the vein, the weight of visible gold was underwhelming, barely 0.2 grams in the best case. Yet the surrounding quartz was rich in sulfides, especially pyrite and minor chalcopyrite. This mismatch raised a red flag. If visible recovery was low but sulfide presence was high, the likelihood of refractory gold, gold embedded within or chemically bound to sulfides, had to be considered. To test that possibility, a more aggressive method was employed: roasting. A portion of the concentrate, mostly sulfide-laden black sand from the sluice tailings, was placed on a steel plate and heated with a propane torch until it glowed dull red. Over several minutes, the sample changed color as sulfur burned off, leaving behind a reddish-brown residue. After cooling, the roasted sample was crushed again and repanned. This time, additional gold appeared, tiny but distinct flakes not present in the original gravity separation. It was the first proof that some of the gold was locked inside pyrite or chalcopyrite grains, invisible without oxidation. This simple test confirmed the need for more comprehensive analysis. Samples were prepped for a lab-based fire assay and an ICP-MS scan, inductively coupled plasma mass spectrometry, designed to detect gold in parts per million, even when hidden inside complex sulfide matrices. While costly, this test is standard in professional exploration and provides a true measure of ore grade. In parallel, a bottle roll cyanidation test was done in field, under controlled conditions. A crushed sulfide sample was mixed with dilute cyanide solution and agitated for 24 hours. The resulting solution was tested with gold-detecting strips. A faint but positive result suggested leachable gold was indeed present, another mark in favor of chemical association rather than just free milling. This introduced a deeper complexity. Refractory gold isn't necessarily a deal-breaker. It's often found in large commercial operations, but it dramatically changes the economics of recovery. Gravity methods won't suffice. Instead, advanced processing like pressure oxidation, bioleaching, or smelting with flux becomes necessary. For a small prospector, that means either finding a processing partner or selling the ore at a discount to a facility equipped to handle it. In this case, the fire assay results were still pending, but all indicators pointed to a vein with both visible and refractory components. That meant grade could be underestimated if only visible gold was counted. It also meant parts of the vein that looked barren, lacking obvious gold, might still be valuable if sulfide content was high. But just as the lab work began to build momentum, a problem emerged. A new sample taken from a promising offshoot vein came back almost completely barren, despite heavy sulfide presence and strong field indicators. It was a setback and one that demanded reevaluation. Was the system inconsistent, or had the earlier samples misled? This reversal forced a hard look at vein zonation, gold concentration patterns, and structural controls. Something wasn't adding up, and it meant the entire prospect had to be reconsidered before proceeding.